the recording again. Okay, so our first speaker, let's say, of today, as for the scientific program, is Ugo Bruzzo from SISSA and UFPB. And he will talk about 3 topics, 40 years, and lots of fun. So please, you can start. Just one small reminder that just afterwards we shall take the first picture of the first photo of the conference. So please, even if there is a break, stay connected, because in the first part of the break we shall take the picture. So
it's a mystery. So
please, Ugo, you can start.
Okay, you can hear me? Okay, so I should say that perhaps I might have the record of who knows Claudio since longer here among the participants, because I met him for the first time when he was my student in a problem-solving class in classical mechanics. It was 1982. So
it was a baby.
We were both, perhaps.
2 babies.
And yeah, so it's exactly 40 years ago. And actually, I wasn't Claudio's supervisor for his tesi di laurea, but then I was his supervisor for his PhD thesis in Genoa. And then after that, we started collaborating. And
before that?
Before what?
Before the thesis.
Well, no,
during the thesis.
Yeah, during the thesis, right. But in that case, I mean, I was your supervisor. Then I wasn't.
Of course.
So that was technically.
No doubt.
A true collaboration. And so I decided to we have at least according to MathSciNet, we have 37 joint papers. They can more or less grouped into 3 topics, at least most of them. These 3 topics are supermanifolds, Fourier-Mukai transforms, and frame sheaves and the representations of quivers. Related to collaborations that we had in these temporal windows. And I would like, in my contribution to this workshop, I would like to give some idea of what we have been doing, so to highlight Claudio's strictly technical scientific work, in mathematics. I should say that some of these, I chose an approach in which I more or less tell you about what we got in that moment. So some of these results nowadays may appear kind of obsolete because perhaps 30 years have elapsed after that. And for instance, our work in Fourier-Mukai transforms definitely nowadays can be framed into some more general setting. So the approach is partly historical, perhaps even archaeological. Okay, and then my approach will be from sometimes hand waving to sometimes a little technical. Okay. So I divided my contribution into these 3 topics. So the first will be about supermanifolds, and here I would like to give some historical perspective to supermanifolds, why they were introduced. And they came from the idea of introducing these geometric objects comes from physics, came from physics. At the time, by the way, I didn't know about this paper by Miyazawa, which probably is the first paper containing a mention of a supersymmetry, although it's completely different from supersymmetry as we know nowadays. It's about a symmetry of baryons, and was absolutely ignored by the physical community. On the other hand, this wasn't the case with the first supersymmetric quantum field theory models. And here I wrote some names, and perhaps the easiest model to discuss is the one by Vessa and Zumino, which appeared back in 1974. And here we have the idea of supersymmetry, of course, is that you have a symmetry which mixes bosons and fermions. So it mixes particles, if you want, with different statistics. Bose-Einstein on one side and Fermi-Dirac on the other. And in this case, we have three fields. We have two scalar fields, phi and f, and we have a spiral field chi. And the idea, as you see, is that these are here in view in the middle of this slide, are supersymmetry transformations, and they are in infinitesimal form. And you see that, for instance, the variation of the boson phi is proportional to the fermion. And it's described by a parameter, epsilon, which is supposed to be odd in some sense. In particular, it satisfies anti-commuting relations. On the other hand, you see that the variation of the fermion is proportional to the boson, actually to the derivatives of the boson. And then you have an additional field, again, bosonic field, again, whose variation depends on the fermion, and again, depending on an anti-commuting parameter. And this is just to make, for instance, this Lagrange, you said this Lagrange is very easy. It has a massless Klein-Gordon piece to start from, then a Dirac term, and then a very simple non-kinematic. I mean, there are no derivatives in the term for the field F. This makes this Lagrangian invariant under this, well, and the related action function is invariant under this supersymmetry. So for supersymmetry, the idea of superalgebra originated, and actually what happened is that if you consider not only this supersymmetry, but also the translations, you get indeed a structure of a super Lie algebra, right? Where together with the commutators, in this case trivial vanishing, you also have an anti-commutator which closes indeed the superalgebra. And then the idea, for instance, proposed by Salam and Stark-D, was to introduce an extended space-time to give a geometric framework to this kind of symmetry. So the approach is very simple-minded. There's no refined mathematics in it, but the basic idea is that you have something which has both usual coordinates x and also anti-commuting coordinates theta. And this gives origin to the notion of supermanifold. And for instance, it can be used very easily. This might be a motivation, physicist motivation why superspace is useful, because you see that a single scalar field, but depending on both even and odd coordinates, simply by making a polynomial, I mean, Taylor expansion in the thetas, which is finite because anti-commutative of the thetas, kind of unifies the treatment of the three fields of the Wess-Zumino model. But then a rigorous piece of mathematics was developed starting from these ideas. And for instance, there was what at the time was called a shift theoretic approach. This is due to Berezi-Leites back in 1974, but then it was rather It was further developed and formalized by Constant in 1977. And here, a supermanifold is thought of as a pair XA. X is, I mean, something you decide what it is according to the category you want to work in. So if you want to do differential geometry, if you want to do complex geometry, if you want to do algebraic geometry, for instance, if you want to do differential geometry, it's going to be a differentiable manifold. Of course, the differentiable manifold or the scheme or whatever comes with its own structureship of functions, which here is denoted by OX. But A is supposed to be the structural sheaf of the supermanifold as such, so it's a richer object. It is a sheaf of Z2 graded commutative algebras, and the Z2 comes from the fact that we have this, we are going to have these thetas that anti-commute, and the relation with the underlying manifold X is the fact that you require that if you quotient out by the nilpotence of A, you obtain the structural sheaf. And moreover, you might like that your sheaf is A, is locally something you have control on. So for instance, you may require that the quotient n over n square is a vector bundle, is a locally free sheaf, a locally free OX module, which of some rank, which is going to be the odd dimension of the supermanifold. And again, locally, this means that this sheaf is generated over the usual functions by an exterior algebra. And the thetas may be regarded as the generators of the exterior algebra. And as such, you see you have the anti-commuting relations we are interested in. Supermanifolds, from the point of view of, I don't know, algebraic geometry or the sheaf theoretic approach to geometry, is a ringed space. So it's something which is not only characterized by a geometric object, but also by a ring of functions. Therefore, geometry can be developed along the paradigm of algebraic geometry, as it was done by, indeed, Peresi latest, Constant, and many more people after that. On the other hand, there was an approach which was preferred by physicists because it was supposed to be kind of easier to grasp. So the idea is that why don't get something super by replacing the real numbers with the Grassmann algebra. So whatever this means, okay? So of course this must be formalized in some proper sense. So R, the real numbers is replaced by a Grassmann algebra with some number L of generators, and the C-infinity functions, usual C-infinity functions, are replaced by some sheaf of BL, some sheaf of BL algebras. But this approach suffers from some drawbacks, which I'm not going to deal with. It was a kind of unsound from a mathematical viewpoint, and actually a sizable portion of our work on supermanifolds has been to fix these drawbacks and out of this idea to make some rigorous piece of mathematics. And well, this is just part of our work on supermanifolds, and also what I'm presenting now is a kind of arrival point of our works on this specific problem. So this was done in collaboration also with Daniel, Fernando Sliperet, and Vladimir Pestov, and some ideas were taken from previous work by Mitch Rothstein. So the idea is to say axiomatically what a supermanifold is, and so we have some ingredients in our theory. So we have a manifold and our topological space that we like to be Hausdorff and paracompact as usual. We have indeed a graded commutative Banach algebra, is like something more general than just a finite dimensional Grassmann algebra. We have a sheaf on M of graded commutative B algebras. We want it to have the identity. this P algebra, and then we want in some sense to make contact with the underlying manifold from a proper geometric viewpoint, and then we ask that from A to CB there's a sheaf, there's a morphism, sorry, from A to the sheaf of a continuous functions with the values in B. So this replaces the procedure of modding out, generalizes the procedure of modding out the nilpotents in the case of Berezin lightest constant supermanifolds, which are a particular case of the axiomatics I'm going to describe. And then it's quite natural to consider the derivations of the sheaf A. We can also these are graded derivations, of course, and then we also take the dual with respect to A. And then the idea is that we want to have some nice tangent or cotangent bundle. So this means that this sheaf, der star A, is supposed to be locally free, a graded module over A of rank Mn, which means that we have an even dimension M and a node coordinate N. And we want this to be locally free in the proper sense. Namely, this means that locally on some open sets U, we have even and odd sections of this sheaf A, such that the differential, suitably defined, in more or less usual way, are a local basis for the sheaf, the dual to the sheaf of derivations. And then in this way, we get what we may call a coordinate cart for the supermanifold. And this implies that the tangent, so to say, the tangent sheaf, the sheaf of derivation, is indeed locally free and generated by the derivations dual to these differentials. Then we want to make contact with the topology of the underlying manifold. So we ask that if we evaluate this morphism using the morphism tilde that we have among our ingredients, we want this to be to make our manifold locally homeomorphic to BMN. BMN is the standard graded module that you make out of B, which is a graded algebra. So it has indeed an even and an odd dimension M and N. Then you want to be able to do some analysis with this stuff. And for instance, one way is to ask that there is a Taylor expansion where for a section of A to take value at a point means first you evaluate with a tilde morphism. Now you have let's say a true function with the values in B, and then you can evaluate it. So this gives meaning to these terms x tilde I z and y tilde alpha z that we have here. And so you ask that there are germs G and H such that you have this Taylor expansion. Then basically you want that your functions are defined by the value that they take after evaluating a differential operator of any order. So you want that if a function is scaled by all differential operators, then of all orders, including zero order, you want the function to be zero. And finally, the final touch, which is very important for further developments, is that you want that this extended structural sheaf A is topologically complete. So again, using the evaluation of morphism tilde, you define a family of semi-norms. So here, this family is labeled by the compact subsets K of the manifold M and by the differential operators L. Okay, and so this looks like the usual semi-norms you can put on, say, the structural sheaf of a differential of a Banach manifold, but it uses this evaluation morpheme tilde, and you want that these spaces of local functions are complete with the topology induced by this family of semi-norms. So this completes the axiomatics. In particular, the last thing I said basically means that locally the spaces A of U are graded Frechet algebra. And actually, this axiomatics yields a category which is well behaved in the sense that all standard geometric construction you might like to make, such as, I don't know, considering vector bundles, connections, groups in this category, Lie groups in this category, so Lie supergroups, representations, I mean, any kind of geometric and algebraic construction you want to make using these objects should be well-founded. This theory is a kind of encompassing because if you, for instance, for B, you choose, this is the graded Grassmann algebra we are using, coefficient algebra, so to say. You may take R, and with some other choices, you exactly reproduce the Bérézine latest theory. If B is a C and you choose some holomorphic complex analytic version of the structural sheaf, you have a complex analytic version of the Bérézine latest theory. If you take for B a finitely generated Grassmann algebra, again with some further choices, you get the theory of G supermanifolds, which we had introduced earlier as a kind of minimal fix of the DeWitt-de Rogers theory. The DeWitt-de Rogers theory is this more topological and physically oriented theory that was introduced at some point, but I mean, it was kind of suffering from some inconsistencies. And indeed, as I was saying, a lot of things may be developed within this framework, and we did that. And now, of course, I don't have time to speak about everything we did in this collaboration with Claudio, but we also wrote papers about some kind of physical applications to supersymmetric field theory. This was done also in collaboration with Gianni Landi. And for instance, we were studying something about the structure of the supersymmetric field equations, in this case from a classical viewpoint. And also we studied something about the consistency of anomalies of a supersymmetric quantum field theory. It turned out that applying some supermanifold techniques could strongly simplify what was done in mathematical physics to deal with these objects. I mean, the anomalies of supersymmetric quantum field. Okay, so this is more or less a very quick and survey of what we did with Claudio and other collaborators concerning supermanifold. I hope I conveyed some ideas. And there is some saying that when you are over with doing research in a field, probably when you are really bored of what you were doing, to close this adventure, this period of your life, you write a book. And indeed, we wrote a book, this book on the geometry of supermanifolds. And so, I mean, this is the epilogue of the first act. Now we go to the second act, namely Fourier-Mukai transforms. And actually, now I will start again with trying to put our, to put our interest in this topic into some perspective. And the first work about Fourier-Mukai transform is due to Mukai. And it was about, it was something which was done using abelian varieties. So we have an abelian variety, which may be thought of as a projective variety, which is also an algebraic group. It happens to be the quotient of spaces En by a non-degenerate lattice, provided that some algebraicity conditions are satisfied. Okay, otherwise you just get a complex torus and not an abelian variety. And then to any abelian variety, you may associate a dual variety, which is a modular space actually, because it is the space of line bundles on X of degree 0. So points of X hat correspond to geometric objects that are line bundles on the original abelian variety, line bundles of degree 0. As such, X hat is a kind of bunch of line bundles. And for that reason, on the product X times X hat, you may define a line bundle, which is in a sense all these line bundles together, which of course can be defined in a much more refined and subtler way. It's a universal object. And in particular, it has this property. It has a line bundle on the product such that if you restrict it to a product of X times a point in the dual, so this is a copy of X, but it will remember the point of the dual, this restriction will be the line bundle described by psi. Psi corresponds to a line bundle, which I call L psi, and the Poincaré bundle has this property, kind of tautological property. And the idea of the Fourier-Mukai transform is to use this object P as a twisting object inside a transformation which takes you from, and now I'm going to be very imprecise here, from a coherent sheaf on X, so a sheaf which satisfies some properties, to a coherent sheaf on X hat. So the idea is that you pull the sheaf back to the product, you twist by P, and you push it down to X hat. This formula, if taken literally, I mean, it may be made correct, but interpreting the objects in it in a slightly more general way. So for the moment, if F is just a coherent sheaf, this may not be particularly well. I mean, the formula makes sense, but it's not really what we have in mind. By the way, you might ask why this is called Fourier-Mukai. Of course, Mukai, because it was introduced by Mukai, but what about Fourier? What's the reason why we mention Fourier in this connection? Look, that this is a kind of similar, in an absolutely formal way, to what you do when you compute a Fourier transform, right? Because you have a function of X, which may be thought as one copy of R, and then you consider it as a function on the product with another copy of R, where the coordinate now is K. You multiply by the function exponent of ikx, and you integrate over X. And what remains is a function of K, right? Which is the Fourier transform of F. So you see there's a formal similarity between the two constructions, which motivates the term Fourier in Fourier-Mukai transform. And then what are we talking about? No, sorry, I have another slide. The other slide tells, I mean, just a justification of what I was saying. Actually, this can be made very precise and correct and deep by, as Mukai already did in his paper, by introducing something more general than coherent sheaves. Namely, we use the fact that the category of coherent sheaf is abelian, and then we may take its derived category. And then actually the objects of the derived category are complexes of sheaves, and actually with the Fourier-Mukai transform, you act on a complex of sheaves. Pull it back to the product, you twist by the Poincaré bundle, and then you go to X hat by taking the derived image. not just a direct image. And this produces a very nice object, very nice functor actually, which happens to be an equivalence of the categories between the direct category of X and that of X set. So why are we talking about this stuff? That's because with Claudia, we answer to perhaps a natural question: how can one generalize this? For instance, considering other varieties in addition to abelian varieties. And actually, it work with K3 surfaces was Claudio's idea, and we did something indeed about writing a Fourier-Mukai transform on a K3 surface. K3 surface is a two-dimensional, complex two-dimensional object. So it's a compact complex surface, which may be algebraic or not, actually, which is simply connected, and also it has a trivial canonical bundle. So you have on it a two-form, holomorphic two-form, which has no zero, right? This is trivialization of the canonical bundle. K3 surfaces are quite close to abelian surfaces for at least two reasons. Actually, they are the two compact, there are two kinds of compact hyperkähler surfaces, provided according to whether you want it to be simply connected or not. So such varieties, if simply connected, are K3 surfaces. If they are not, they are abelian surfaces. This is one reason. And another reason is that a class of K3 surfaces called Kummer surfaces can be obtained by starting from an abelian surface, which is a natural involution, which is basically taking minus the identity, the action of minus the identity in the group, because an abelian surface is also a group. You take the quotient, you get something singular, you desingularize it, and what you get is a K3 surface called the Kummer surface. So it's not so strange to think that perhaps something should work if you try to generalize or to consider a Fourier-Mukai transform from K3 surfaces. The price you pay here is that you have to make some choices, and I think that we were so basically we built on an idea in the original in a paper by Mukai, which basically only defined the homological ghost of this Fourier-Mukai transform, namely what the Fourier-Mukai transform induces at the level of cohomology. We define it as a functor between the direct categories. And so this is our model. We assume that the K3 surface has two classes, cohomology classes H and L, satisfying some properties. I'm not going into the details, also because I see that the time is running. I start at past 10, right? Valerian. Okay, so we have two classes. H is going to be ample. So it's a divisor which would define a projective embedding of the K3 surface into projective space. And then we ask for some numerology. When you have algebraic homology two classes, you can intersect them. And we want these intersection pattern to take place, right? H square is 2, H times L is 0, H square is minus 12. And then we want this line bundle given by the first channel class 2H plus L as no sections. Kind of technical reasons necessary for the theory to work. And then you see we take a modular space of mu stable sheaves. So what are these mu stable sheaves? Suppose you want to build up a modular space of sheaves, and then you realize that these sheaves have a lot of automorphisms, so they are not going to produce a modular space which is an object in a nice category, for instance, schemes. You can do that, but you have to enlarge your category, for instance, introducing stacks. If you don't want to do that, you might like to rigidify your sheaves so that they have much less automorphisms, much fewer automorphisms, and then you may construct a good modular space. Stability is exactly one of these conditions, in particular stability. I'm not going into that. And in particular, if you want, the modular space comes with several components, and you try to consider some given component of this modular space. So you fix topological invariance of the sheaf. And here we fix the rank to be 2, the first Chern class to be L, and then something related to the second Chern class, which is the rank plus the second Chern character, is going to be -3. So you consider this modular space, and it turns out to be a very nice object, which is again a K3 surface, which happens to be isomorphic to your original K3 surface. So in this way, our original K3 surface may be thought of as a modular space of objects over itself. And on the product, there is a locally free universal bundle, a generalization, I mean, something which plays the same role as the Poincaré bundle in the case of a billion varieties. So it's the universal family of the sheaves that are in this modular space. It's a bundle because actually in this case all these sheaves are vector bundles. And this is a kind of evolution because again, if you do it twice, of course as a variety you get the original variety again, because at every step this is an isomorphism, but it's also an evolution in the sense that this is compatible with this modular space structure that we have on it. And then, mimicking what was done by Mukai for a billion varieties, one can define an integral functor, and again to get an equivalence of categories. And for instance, what can we do with that? This is what I was saying. You see this diagram in the upper left corner is what I was saying, the fact that this functor actually has a kind of underlying, defines an underlying morphism between the homologies of the two spaces X and X hat in such a way that when you transform an object in the derived category of X, which has some Chern character, let's say, the transformed object will have a Chern character, not exactly a Chern character, but something very close to it, which is given by this morphism small phi. Okay, and then, well, you have some conditions according to which if you start, you see, objects of the derived category are complexes of sheaves, but you may consider in particular a complex which is made up by a single sheaf, let's say sitting in degree 0 in the complex. And then you may ask for conditions such that the transformed object is again a complex consisting in one sheaf, perhaps not sitting in degree 0, sitting some other degree, but anyway a single sheaf. And in this case, it is known that we proved that this Fourier-Mukai transform preserves the stability. So it will map a modular space of stable sheaves to another map of stable sheaves, which was already known for a property which is already known for a billion varieties, and perhaps may be regarded as a foundation of the origin of idea of looking for a stability condition, not for sheaves, but rather for objects in the derived category. So this is the first idea in mathematics is due to Bridgeland. Here in the audience, we have a great expert of this stuff, who's Emanuele Macri, who will speak later in this conference. And also this was taught of by physicists. Now here I cannot really say who was first. If the physicists took some ideas from Bridgeland, or if mathematicians took some ideas from physicists. Anyway, this stability notion in string theory is called pi stability. So we have also some input from physics for sure. And we also worked on the differential geometric side of this transform, and actually, so Mukai's paper was about a billion. Fourier-Mukai and abelian varieties was published in 1980, and I think that there was a paper by Nam published in 1983 where he constructed using some construction that was reminiscent of Matthias Singer's index construction. He defined some kind of transform for instantons on tori. And then it was recognized later by Schenk and Bram van Baal in two different papers, Schenk on one side, Bram van Baal on the other side, that this was actually a kind of differential geometric description of Mukai's transform. And then we tried to do this, was this the case also for KT transforms, or perhaps even more generally? Is there, a nice notion of some form, some kind of transform in differential geometry, which is well defined not only on tori, but in some more general setting. And we worked on this. Perhaps I don't have much time to go through it. The idea is that the right setting is that given by the so-called quaternionic manifolds. So something which is slightly more general than an hyperkähler manifold, on which we may consider objects which were called quaternionic instantons, and which generalize in higher dimensions the notion of instanton, which works very well in real dimension form. So we worked on this, basically defining a transform which is an Matthias Singer index. So if we have a compact Kähler manifold, we X and Y on the product, we assume we have a homomorphic vector bundle with a connection whose curvature is of type 1,1. And then we consider on X, which is, so to say, the original manifold, a bundle with a connection such that when you pull it back, the pair, bundle and connection up to the product, and you couple with the Q with its connection, this satisfies a nice condition. Namely, out of this structure, you may construct a family of Dirac operators. And you ask for, you see, when you have a family of Dirac operators, you associate with it an index, which is an element in the K-theory of Y in this case, because Y is regarded the space of parameters of this family of the Dirac operators. And then defining this index in K-theory means taking kernels minus co-kernels. The dimension of kernel co-kernels may jump when you move in Y, but the difference is constant, the difference of the dimension. And then what you do is that to have a viable theory, you kill one of the two. You make a geometric assumption such that, for instance, the kernels are always 0. In this way, the index is a vector bundle on Y. And then you can make, you can check that on this vector bundle, you can define a complex structure, and you can define a connection. You can define an Hermitian metric, so you get, you get something which you look as the Kähler-Nam transform. This is the name we chose, the Kähler-Nam transform of the original bundle with connection on X. And then you have something which is similar to the proof about the preservation of stability under the Fourier-Mukai transform, which says that if you have quaternionic instantons on X, this transform will map them to quaternionic instantons on Y. So you have a differential geometric analog of the property of preservation of stability under the Fourier-Mukai transform. We also made work on the relative free Mukai transforms. Here, really, I'm not going to spend much time. And in here, what you have is that you don't have a variety, but you have, your variety is fibered over a basis B, and you want to make a relative construction. So a typical situation is when X is an elliptic fibration over a base B, and Y is the dual fibration, which typically is the compactified, the relative Jacobian, right? X is a fibration elliptic curves, and Y is the compactified relative Jacobian. And then on the fiber product, in this case, you have a natural object, which in the Fourier-Mukai parlance is called a kernel, and you use the kernel with a formula very similar to what we saw in the case of the absolute transform to define a relative transform. And we work on this quite a lot. And again, when we stopped working on this, the epilogue was to writing a book. It was to write a book, again, with the collaboration with Claudio, myself, and Danielle. Okay, and this leads us to the third act, and this will be quite quick, actually. This is work on frame sheaves and representations of quivers. And I will start by saying what a frame sheaf is. So here the ingredients are a smooth projective variety X, a prime divisor in it, P, and a vector bundle on the divisor. And then we say that a sheaf on the variety X is framed on D to F if there's an isomorphism, the framing, between the restriction of E to D and the sheaf on F. Usually F is a vector bundle, so here I wrote a vector bundle, which of course is bound to have the same rank of the sheaf E. There's a natural notion of isomorphism, simply, isomorphism which are compatible with the respective framings. And for instance, on P2, when the variety is P2, and for D divisor D, you choose a line in P2. This is the original work of, it comes from actually physical instantons, as we are going to say in a moment. This was studied in detail by Nakajima. So you might like to consider the space of isomorphism classes of torsion-free sheaves. So not just vector bundles, but torsion-free sheaves, namely vector bundle, which in some sense may have some singular fibers of some given rank R with second Chern class N, which on our line, which we fixed from the beginning, are framed to the trivial bundle. This condition fixes the third Chern class. This is why the third Chern class to 0. This is why the third Chern class doesn't appear in the topological invariants we are choosing here. So these objects depend only on two parameters, the rank and the second Chern class of the bundles of the sheaves. Sorry, we are parameterizing, and this happens to be a quasi-projective variety of dimension 2Rn. Okay, so it's a smooth variety of dimension 2Rn, which can be embedded into a projective space as an open subset. Not an open subset, sorry. Whose closure is projective in a projective space. Sorry, is an open subset of a projective variety. This happens to be a resolution of singularities for a physical object. An object coming from physics, which is the modular space of framed ideal instantons of indeed rank R and charge N on R4. So these are connections of bundles which are whose curvature is anti-self-dual, which satisfy a fixed behavior at infinity, which is the framing in this case. And then this allows you to define an integer topological property of the bundle, which is called the charge. And these instantons may have degenerations which produce singular points of the modular space. So we get M0Rn, which is a singular affine variety. And then what happens is that MRn happens to be the singularization of this singular variety. This resembles very much what happens with the Hilbert scheme of points of a surface, in particular C2, and the symmetric space. I mean, the Hilbert space is the singularization of the symmetric product via the Hilbert-Shaw morphism. And indeed, this is the particular case that you get when the rank is 1, right? M1n is actually the Hilbert space of zero cycle, Hilbert scheme, sorry, of 0 cycles of length n in C2. And then the space M01n is simply the symmetric space, the nth symmetric space of C2. And actually, the objects of MRN can be described by the so-called ADHN data, right? Coming from Mattia Drinfa, the Hitching Money. They can be described in terms of linear data. In particular, one can show that if you consider pairs of matrices, n times n matrices, and these two vectors, row vectors and the column vector with n components, you assume that these data satisfy this constraint here in the middle, commutator of B1, B2 plus ij equal to 0, and you add the stability condition. It happens that you have a natural action of the general group, general linear group of order n, acting by conjugation on the matrices and in the way it can on these vectors. The stability conditions that I'm not writing here make this action free. And as a result, the quotient is a nice variety, and indeed is the variety MRN. So this is a kind of these are kind of many quotation marks, local coordinates on the space MRN, right, in this way. And actually, this also relates with monads and quivers. For instance, you may see that the elements, the frame sheaves in our OP2, they can always be described as cohomology of a monad. So here we have 3 vector bundles, U, V, W, which are basically, they are fixed, and then you have morphisms between them. Morphisms may vary. And this is supposed to be more than a complex, because alpha is supposed to be injective, beta is supposed to be surjective, but then in the middle you just ask that the composition is 0. And then it makes sense to take homology, kernel of beta modulo the image of alpha, and this happens to be if U, V, and W are chosen in a suitable way, this happens to be a bundle in our space MRN. So this is a kind of another description of our modular space, which actually is an intermediate step towards the description by ADHM data, because the data are indeed encoded into alpha and beta. Alpha and beta encode many things, in particular encode these data, which are here in the upper left corner of this slide. Actually, this data in some sense suggests you to draw a quiver. I'm not going to tell you what a quiver is, so I will, if you don't know what it is, I leave so to say, the definition of a quiver just in a pictorial form. Okay, in this case we have 2 vertices and 4 arrows, right? This make up a quiver. The vertex upstairs, we associate with it a vector space of dimension n, and to the vertex downstairs we associate a vector space of dimension 1, and then in some sense B1, B2, you see The structure of the arrows tells you that you are considering endomorphism of Cn and maps from C to Cn or Cn to C. And then what happens is that if you consider this quiver, it is known that from a quiver you can get an algebra, and you can, with the relations given by the constraints that we are considering, and then you take the modular space parameterizing the representation of this algebra. This happens to be the modular space MRN. So you can look at this modular space of frame sheaves as a modular space of representations of a quiver. And then the question is immediate. What can we do with spaces that are not P2 or something more general? So some work we did was to consider Hilsberg surfaces. I mean, the modular space of frame sheaves, at least in the case of surfaces, always exists, because we checked this together with Dmitry Markushevich. So these modular spaces exist if X is a surface and the framing data are nice enough. So D must be, I don't know, irreducible, smooth, big enough, F perhaps semi-stable on it. The modular space exists, but what about the description with monads, with ADHM data, with the quivers? And what we did was to consider this theory for Hilsberg surfaces, which may be regarded either as a divisor in P1 times P2, given by this equation, or as the projectivization of the total space of the projectivization of this line bundle of degree 2 on the projective line. So we get the nth Hilsberg surface, and then we consider some. Here again, here the function class is not fixed by the framing, but it's also is only constrained. So the function class must be always a multiple of a given divisor, and so it's quite natural to consider this space parameterizing isomorphism classes of torsion-free sheaves on the Hilsberg surface, framed on a line in some sense that we chose, having some topological invariance. And then we proved that this set is non-empty if and only if the topological invariants satisfy this relation. And if this is the case, it is a smooth algebraic variety of this dimension. We did it to represent against the base of a principal bundle, but which has a meaning, of course, but let's forget about it. And this is actually a fine modular space of frame sheaves of Pn. And again, the rank 1 case, first, in the case of P2, the rank 1 case was Hilbert schemes of C2. Here, the rank 1 case is, and zero future class, is the Hilbert scheme of an open part of the Hilsberg surface, which is the total space of this line part. And then we also studied the quiver point of view. We introduced this quiver, at least when n is 2 or bigger. For n equal to 1, the quiver is slightly different. And then we have, you see, ADHM data, which replaces the B1, I, and J, no, of the P2 case. Here we have more objects, satisfying relations, satisfying stability conditions. And what happens is that again, and here, I'm sorry, I just, I pasted this formula from a paper, and of course you see that this rep means a modular space of representations, but it carries a lot of labels. I'm not going to explain what these labels are, but you have some modular space of representations of a quiver satisfying several conditions. Some space, sorry, of representations, and then you take a quotient, and then you can prove, and this is something that we did only for the rank 1 case, the Hilbert scheme of this variety X is isomorphic to any, sorry, I took the wrong sentence. It is irreducible, and it is represented as this quotient. This modular space is irreducible and is represented as this quotient. At first, we couldn't prove the irreducibility, and then we did, and I copied the wrong sentence. I'm sorry. I didn't take the last theorem we got on this. So it is irreducible, and it is representable as a quotient in this form. This coincides with Kuznetsov in the case n equal to, because for n equal to, this space xn, so x2 happens to be the Kronheimer ALE space A1. And since Kuznetsov did this for ALE spaces, in this particular case, we cross its work. Okay, so finally, I'm over. And just a few words. As I was saying, I know Claudio since 40 years. We became friends. We shared a lot of adventures. As Pier Giorgio was saying, not of them we would like to tell in public. And I'm serious, I'm not joking. I don't know if Claudio understands, for instance, one instance of this. And
yes, of course.
We became friends. We shared a lot of dinners, wine, and whatever. And then, therefore, I would like to conclude my contribution to this workshop for Claudio's 60 years, adding my wishes and wishing him a long, fruitful prosecution of his activity, which is so ample and transversal and so multifaceted indeed. Thank you very much.
Thank you, Ugo. If there is any question or comment, please.
Maybe it's a bit late. May I add a few words to Ugo's talk?
Yeah, you can, of course.
Yeah, not of course. No. So thank you for putting in a nutshell almost 35 years of scientific collaboration. I must say that Ugo taught me a lot of mathematics, of course, and a great deal of physics as well. We had many conversations about well, classical mechanics, general relativity, that are the part of physics that I understand better, and also about quantum mechanics and quantum field theory that are part of physics that I cannot understand very well, I must confess. But in any case, Ugo tried to give me some say information, some rudiments on these topics. And well, I must say that I learned from Ugo also to think in a different way about interactions between maths and physics, and not just say in a static way, but in so to think of these interactions as a dynamical interaction. And this had a quite strong influence also on my work, if I say work, on history of science, and in particular about history of mathematics in the 19th century. So I think that many times historians have the, let me say frankly, the bad habit of thinking of interaction between different fields in a non-dynamical way. And so thank you, Ugo, for this. And also I would like to mention another thing that that Ugo taught me. So how to interact. This is the word, interaction. Interact with students, especially PhD students. There are some of them in the audience, and also brilliant laureate students, so at a more or less master level, brilliant students in this case, and there are at least 3 examples in this conference. So the key point is not to interact with this kind of students as say in an authority way, but to treat them mainly as collaborator. This means that well, problems are important, but it can be not a very good idea to give a student a small problem to solve, and very often this kind of small problems, you know very well the solution from the very beginning, but instead try to start with this kind of brilliant students some kind of research project to work together. And this also I learned from Ugo. Thank you.
Thank you.
Okay, so is there any other question for Ugo, or someone want to add something? Okay, so if not, let's thank Ugo again for this talk.
Thank you.